Matt, can you hear us yet? No.
What about now?
Yes.
Hear me now? Okay.
Yes.
Okay, give me one second. Let me figure this out. There we go.
Matt, can you hear us yet? No.
Okay, can you hear me now?
Yes.
Hear me now?
Mm-hmm.
Okay.
Yes. Are we rolling?
Almost. Okay. And we're live.
Great. Well, welcome everyone to the October meeting of the Barnard Astronomical Society. I'm the new president, Amy Hon, and I'm going to walk us through our business meeting first, and then we'll have the program presented by myself and Kevin Hon. So we'll get started with the business meeting. So I'm going to share my screen. That kind of prompts me to make sure I don't miss anything here. And it's going to go crazy for a second. Okay, so first off, I would like to welcome everyone. Thank you for being here tonight. And our bylaws ask for a roll call, and I'm assuming that's just taking count of who's present. I would like for our officers, if they're present, to chime in and introduce yourselves. Our new officers. I can't see anybody on my screen. All I'm seeing is my PowerPoint, so I'm sorry if I don't see you or see a hand wave on the that through the icons. But is Dustin here?
He is. He is not. I believe with it being fall break, he might be out of town.
Okay, that sounds good.
But I haven't heard from him, so it's unlike him not to respond.
Okay, all right. And I believe Janet is here. So Janet, if you want to wave or say hi.
Yeah, I'm here. My voice is gone, but I'm here.
Okay, so Janet is our treasurer, and is Nakota here?
She is not either. I have not gotten in touch with her.
Okay, so we will need someone to maybe volunteer to take minutes for this evening's meeting. Would someone like to be a volunteer for that?
I'll do it, Amy.
Okay, thank you.
Since I'll eventually get them anyway, so.
Okay, and I assume that was Beth I heard talking? Yeah. So Beth does our awesome newsletter. We have dogs barking outside, so we're gonna close that window. And so thank you, Beth, for putting together such a good newsletter for the club. And I really enjoyed this month's, especially with Matt's Orion work in there as well.
I feel like I can't take credit. I feel like Ralph and Matt kind of held that one up this month. So,
well, thank you for putting it all together. And then we have our programming chair, Ralph, and I think I saw him earlier.
I'm here.
Great. Hi, Ralph. Okay, so do we have minutes from the last meeting?
I have not seen them, so I don't know. That's okay. A great question.
So we have a recorded copy of last month's meeting on YouTube, so we can pull some meeting and some minutes. And I had planned on doing that today, but just didn't get around to it. I'm pretty sure Dustin already has minutes from it. He's pretty good about that. But again, I think with it being fall break, it might be it might got off the radar.
Okay. Do we need to wait on the approval of that, or can we proceed?
Yes, they've got to be printed. So next month, what we'll do is we'll print last month's and this month's. We'll make sure they get in there, and after everybody sees them in the newsletter, we can then vote on them.
Great.
Patrick had been just putting them in a slide as for folks to see during the meeting. That's due. No one had a problem with that, but I always like for them to be in the newsletter, just so it's a written account and shows that the society's got a record of things.
Yeah, I like that as well. Okay, we'll do. What was that?
I said I'll send you a copy.
Oh, okay, great. Thank you. Okay, moving on to the financial report. Let's see. Janet, do you want to speak to this, or do you want me to just review it? I pulled this from the newsletter, so I don't know if there's any additional information that we need to know.
No, I haven't added anything since then.
Okay, so it's pretty straightforward as shown. In September, we had 1657. We added a couple of members and believe had a few renewals. So we've got the membership credits and then the deductions for the Astronomical League, Whereby, and the Meetup apps. And then that leaves us with $1,489.95 as of October 5th.
I had a quick question.
Mm-hmm.
I saw the PayPal, the membership, and it's not my question. I should say someone wrote into the Facebook page and asked the question, but it was concerning the dues on the Facebook page when you go to join. Instead of them being $35, which was the original thing, they're $37. I'm assuming those $2 are the costs involved.
Yeah, that's the fee.
Okay, no problem. We might want to put that someplace, and I'm not sure where we can do that. I can talk to Grant if I need to have them change the wording there. Did you do that, Janet, or did Patrick do it?
Somehow, accidentally, I did it. I didn't think I had. Somebody found it and questioned me about it.
Way to go!
Yeah.
Well, if you'd like to see if you could just add something that last $2, that's what that's for, in case anybody asks.
Okay.
So.
Great. Are there any other comments or questions? All right. Moving on. So our membership, we have 2 new members. And so we're at a total of 90 members. And of course, we thank everyone who has joined and renewed. We look forward to maybe getting some new members here in the next months. And I have received no correspondence. I don't know if anyone else has to read to the group. So I'm going to move on to the next, which was unfinished business. So I heard Patrick, is there any unfinished business we need to discuss from the last meeting?
Not that I'm aware of. I tried to leave it so that we didn't have anything. I mean, there were things that I was thinking about starting, but I intentionally didn't because of that fact. So no, not that I'm aware of.
Okay, all right. And then, so we'll move on to new business, and I've kind of joined this with announcements. Does anyone have any new business they would like to bring forward or make any announcements?
I mentioned this to Ralph, our program chair, and Amy, I think I mentioned it to you as well, but we had a person reach out to us and ask about a potential program and concerning light pollution. I can forward you the email, let you look through it, see what you think, and maybe we can start some correspondence there. But maybe something we could do.
Okay. So this is a program not as in like the after business meeting program, but actually a program like an initiative by the group, or
no, it's a after business meeting kind of program. Okay. I believe it might be a little bit longer than that. Give me 1 second. I'll read you the email that I received concerning the project. And they have a local connection, which was one of the reasons I saved it, thinking that it might be of interest. And it's buried in my email box. Oh, there we go. Well, sorry, I'm trying to find the beginning. Okay, I'm sorry. It's in here. It's been truncated. I can't tell what's what. So come back to me.
Okay. Yep. That sounds good.
I have two things,
Yeah.
Amy. One is that we should get the budget prepared probably for next month so that we can vote on that and implement that at the beginning of the year. And the second is I have a bunch of equipment. I have a large telescope, the 16-inch telescope in my garage, and I don't use it. I would like to get it out of there. So if someone is interested who will use it, I really like to pass that on to somebody instead of have it collect dust. And if not, if nobody wants to use it, if we would like to sell that and donate that money to the club.
So
Okay.
that is a 16-inch Orion telescope donated to the society by Bill Seymour, and we had initially planned to store it out at Harrison Bay. Of course, when the pandemic hit, everything changed. We had some reservations about storing it at the observatory, of course, but I don't know. That's definitely a conversation we need to have. And it's lived at Ralph's house, and now it's lived at Patrick's house, and it's going to need to go someplace else.
Kevin, clean out the crawl space.
It is a really nice telescope. It is essentially
It is a nice
Richard.
telescope, but it's a monster, and I'm wondering if we might be better served selling that and buying something else for the club that's a little more portable and easy to use. Because it sat at Ralph's house for I don't know how many years too. It's just large and bulky, and if it's going unused, then it's really a useless asset. So if there's some other way, if somebody's willing to do that and use it for the club, great. After dealing with the first time, I was like, this is just very difficult to bring to the star parties. We don't have star parties now really very much anyway. So it's just something, an asset that it's nice, and we think it's great to have it, but we haven't really used it in probably 2 or 3 years anyway, I would guess. Ralph might know better than me, but I know it's been in my garage for 16 months.
Okay. Yeah, let's
Like I said, we have a bunch of, we have
Yeah.
telescopes in the basement.
And I have
too.
some boxes of other stuff as well.
Okay.
I'll write that up, document what's there, and then we can figure out what we want to do with it. But I would like to get it out of my garage.
Okay. We'll communicate.
Okay.
Okay, good. Other business. So, in thinking about some past conversations that we have had, that in meetings I've been involved with, and some things that I would like to see the club do going forward, and also accommodating traditional things we do, but to kind of change it because of the COVID situation. I was wondering if there were people who might be interested in kind of being on a committee. And so I've thought of these 3 things that I think we need to look at that would help to benefit our society in the long future and also in the short term. And one of these would be a small group of people who might be interested in really looking at the Astronomical League benefits to the club and making sure that we are taking full advantage of what's offered to us as a club, and kind of catching us up on that and getting us in a position to where we're more active and that our dues money are actually going towards activities and benefits to the club and our relationship with the AL. So, for example, there's an opportunity for a club member to be an AL correspondent, and they work with the regional astronomical league to tie the club to the regional group, and then we get the benefits from that communication. So I'm interested to hear if anybody would be interested in being that correspondent. And also I've read up about, briefly, I haven't delved into the Astronomical League, all the benefits there and all of the opportunities, but there's also these wonderful opportunities as ambassadors with NASA and the Jet Propulsion Lab that could benefit some of our members, especially drawing in younger members and bringing in, recent graduates, college students who have a connection to NASA and can bring that information to the club as an ambassador. So that's one group I'm looking for maybe any interested parties to maybe contribute to. The second is just a general outreach group of one or more people who would be interested in seeing how we can extend our outreach to the community. And especially when we're considering how we're working in the virtual world and how we have opportunity to reach into households. So where travel may be limited just normally, keeping people at home, but how we can provide more outreach to our community and bring people into our membership that wouldn't normally be a part of our club. And then finally, if there's anyone interested in maybe coming up with some alternate ideas for the Christmas party. So I labeled it a virtual Christmas party because I think for safety reasons, that's the avenue we should take this year. But I think there's some maybe fun and creative things we can do as a group where we do spend that time together and kind of take advantage of, again, the virtual world and having a bit of Christmas fun.
We can rent
I'm not gonna
hamster balls and roll around and stay socially distanced in hamster balls.
Those big bubbles.
Just real quick on your first two topics, I'm also a member of the Raleigh Club, and I know who the Alcor and the outreach coordinators are for that club.
Yeah.
If you want me to see if I can get them to speak to the club about that, I can certainly try to arrange it.
Who's speaking? I can't see faces.
John Sadler.
Okay.
Yeah. So, I know that they have the Raleigh Club has a pretty active outreach. Obviously, this year is a shot for everyone with all that. But they also have a very active Alcor representative who coordinates all that and hands out the awards and such that you get through the Astronomical League at club meetings and stuff. So there are, I'm sure they would be willing to speak if they're available on some time, but I can certainly reach out to them and ask.
I think that would be great. Do you want to kind of maybe head an effort to make those connections more and see what we can do as a club to be more active in that area?
Well, I can certainly ask them, for pointers. I don't know if I can dedicate to actually doing anything other than arranging them, to get here right now. But I certainly can reach out to them and see what. I know that I'm pretty sure Doug in particular would love to speak about Alcor. He's a big fan of that. And outreach, obviously, this year's just been a terrible year for that for everyone. Mm-hmm. But I know that they would be probably willing to speak as well about some of the things they do with outreach.
Great. Yeah, that's great.
I know one of the things that they do is they have a email list that goes to people that are on an outreach committee, essentially, where people can email in their requests for us to do things. Mm. So that's kind of the first step, making something available, saying, hey, if you want anything, email this list with the details and we'll see what we can do. Because, Boy Scout clubs and things of that nature, they tend to, want to have astronomers there so that they can, sometimes there's badges and stuff that are on the line. So, they get all gung ho. So,
yeah, that's great. That's great. If anyone else is interested, we could probably I could write this up for the next newsletter because I know there's some people who aren't joining us at the meeting that may read the newsletter, and I can write up a request if anybody's interested on sitting on any of these committees and working on these things to let me know, and I can kind of join people up to maybe get that going. I think. Does anyone have any comments or questions?
I was just going to say, I think a piece of that will actually be.
I was going to say, I was the AL coordinator up to about 5 or 6 years ago, and then it's a really fun job to do. You get to check people's when they're having doing their awards and things, and and really it's not a hard thing to do because all you have to really do is bring the correspondence from the astronomical lead and take anything back to them. This is George Bell.
Okay, thank you.
I was the AL for many years, and I enjoyed it a lot. It was a lot of fun. You get to check. I don't know. In recent times, there's not been a lot of people doing a lot of the awards. For many years, a lot of people in the society were doing a lot of those observing awards that the AL publicizes, and it was a lot of fun to check those. It really would be a good thing to get people doing again because it's a good thing to go out when you take your telescope out and you look at the Orion Nebula, look at Saturn. But when you're working on those awards, it makes you find things that wouldn't normally look at, and it's really good. They're really good. So
a lot of people just don't know those awards exist. And it just requires some modest documentation. To qualify in most cases. I mean, there are some that are more technical, but I don't know all the details.
I think everybody ought to have at least the Messier Award for just as almost have to be a membership requirement.
Yeah. Well, a lot of people don't realize that there's a binoculars award.
Yeah.
You get a reserving award for binoculars.
You can go on the AL website and you can see all the members of our club that have gotten those awards.
Oh.
It's very interesting to see, and a lot of them are still active. So, but I haven't seen anybody getting those awards in the last few years. So,
and I think that's something we could really tie into right now with all of our online outreach, bringing those types of offerings to the public. Once you join, here's something you can do, and offering those walkthroughs for binocular object. Observation, things like that. I think one other piece, Amy, I was just going to mention that we already have some fantastic contacts in the community through the Hamilton County School Board, the local parks, Cloudland Canyon and Harrison Bay. And so whoever that committee ends up being, a lot of the work is already done, but it really is just a matter of shoring up these connections in committee form so that as we grow, we can manage it easier. Because right now, like when we go to Cloudland Canyon, it's usually one or two of us that have the connections that call. But it would be great if there was a committee that was on first name basis with these groups. So I guess I want to emphasize that you're not recreating the wheel. This society already has wonderful outreach. So we're really just kind of forming up what we've got and then adding the components for the Astronomical League, which I think is fantastic. I'm just so happy that's coming back.
Yeah. Well, great. Yeah. So if anybody's interested in getting involved in these ways, please let me know and we'll get rolling on it.
I can certainly create an outreach list committee on the Groups IO list server. And we can start putting people in that and having discussions in there. If we decide to go that route, just let me know if that's what you guys want me to do, and we'll set it up, see who's in it.
Great.
And just a real quick matter of housekeeping. I'm sorry, Amy.
No.
John, we have had a ton of new memberships here recently, and I just want to make sure we don't miss anybody in terms of getting them in the Groups IO. So I know Patrick has been really good about getting that stuff to you. And I think just in this transition, we want to make sure we don't drop anybody or miss anybody. So
I'll show you guys what I'll do is if you want at the end of this call, I can even walk someone through it if you want. Basically, all we got to do is get the list of email addresses and send out invites to them. And the nice thing about it is if they're already in there, they won't get another invite. So if we have existing members that haven't joined, we can just blast them again with it until they eventually get the hint and join the group.
Yes.
So I'll show. So I'll gladly show you guys how to do that because I shouldn't be the linchpin on that. I would like you guys to be able to do it without me if I'm off in Bermuda or something.
Right.
So,
well, you set me up as an admin, so now I can add and take away, and so it is finally working now. So thank you. But I just want to make sure we don't miss anybody. I just got a text from Dustin. He is taking his final in his master's classes. I was blowing up his phone today. So anyway,
Okay.
That's where Dustin's at.
Education's overrated, isn't it? No.
Beth, did I hear you try to chime in earlier?
No, it was me, Janet.
Oh, Janet, I'm sorry.
Yeah, the Astronomical League still has George Bell as the Alcor. I take it you're not doing it anymore.
Really, there hasn't been much activity really in the Astronomical League lately with our club. For many years we were very active, and then all of a sudden everybody just sort of seemed to ignore it. So I would like to see it get active again. I don't mind being on the Alcor committee. I'd really like to because I'm a real proponent of it. I really think these awards are something that, like I say, a lot of people don't keep up with it, and I think they're really good programs. And if you complete these awards, you've really learned a lot. So I think.
Go ahead.
Yeah, I'll be glad to be on the committee.
Okay.
Yeah, from what I remember about the Alcor, and I could be wrong, I could be crossing my streams here. The rates that the club has to pay to Alcor depends on the membership list. So if we've got a small membership list that's on there and we haven't updated it, we may be paying more than we need to be. Because
we've updated our list, I'm sure.
Okay.
Yeah,
good.
I send them one every 3 months. It goes by percentage. And
Yeah, they seem a little persnickety about it.
Yeah, because we have so many associate members, that's what screws up our percentage.
Yeah. And it is a big thing that we haven't been active in, and I don't necessarily think that's a bad thing. I think our society went through a shift, starting with Richard. I think Richard kind of moved us, and thankfully, because of Richard, moved us into a more online mode of community outreach. And so now it's time for us to go back to our roots and really kind of solidify those things. But George, I know that I would feel so wonderful about you helping out and getting us going. And, you've got a wealth of knowledge that none of us have. So any help you're willing to provide, we will take it.
Absolutely. Okay. Any other comments or questions on this before we move on? Great. Okay. Any announcements?
I got a new car.
Yeah, who got the telescope that invited the storm? Okay. So at this point, I believe the business meeting is coming to a close. So we need to officially adjourn. Do we have a motion?
Motion.
And a second?
A second.
Great. All right. All in favor?
Aye.
Any opposed to closing it?
Aye.
You don't need to do that. Ned'll tell you that, but
Okay. All right. So at this point, we will move on to the program. Can you hear me?
yeah.
Okay. I'm pushing buttons and I'm not seeing. Okay. We got a transition here. So we have a cat that's decided to chime in just in time for the presentation. So tonight's program is by me and Kevin Hon. And let me get this going, this new presentation. So here. Okay, can everybody see that?
Hey, Amy, if you click that little hide tag next to stop sharing, if you can see that. There you go. Perfect.
Thank you. All right, great. So I'm Amy Hon. I am a professor of geology at UTC.
And Kevin Hon, I'm a geophysicist at a local consulting firm called SNME.
And we were asked by Ralph to talk about the moon. And I'll admit, I'm glad he did, because I've learned a lot putting this together. It turns out I knew pretty little about the moon in terms of geology. I tend to focus my attention on Mars. So thank you, Ralph, for asking us to do this. So I'm going to let Kevin start us off.
All right. The formation and geology of the moon. Hint, it is not made of cheese. So just a kind of a general presentation outline here. I'm not going to read through it, but just to kind of take you through the topics that we're going to kind of hit up on here during our talk. So as first, the moon, just the facts, just some basics. Just again, I may not read through these as well, but the moon's quite a bit of a distance away from us, and it has a variable orbit and rotation compared to the Earth, which is pretty cool. And just things about mass, and of course it's much smaller and lighter than the Earth, and as we've all seen us bouncing around on the moon as astronauts, the gravity is quite a significant difference. And I just like 100 pounds on Earth is 16.6 pounds on the moon, which is pretty crazy to really think about that. And the temperature differences are just outstanding. And this is, I didn't know that it's actually slowly moving farther away from Earth. And then of course it doesn't move. It seems like, it should, but it's not. It is tidally locked with us. So you only see the one side. And as you'll see earlier, it was a long time before we actually saw the backside of the dark side of the moon. So before space exploration, so when did we first observe the moon? When we first looked up, of course. But like some other kind of interesting things, of course, the moon's been known for folklore and just throughout, history and science. It's just really interesting on how things develop and what is this big ball in the sky. And I'm going to butcher a lot of names here, but in ancient Greek, his name was Anaxagoras. But what's really cool about that, he actually realized and determined that the moon doesn't actually shine by its own light, that it's a reflection from the sun. And then again, in 150 BC, the Greeks were just great scientists, and I'm Seleucus of Seleucia actually realized that our moon causes the tides that we have on Earth. And then huge jump. You could almost say like the Dark Ages on new and exciting things outside of folklore, but from the science of things. The telescope. I mean, Galileo was the first, or one of the first, to actually point and make an observation of the moon using a telescope. Kind of skip forward a little bit. In 1647, finally seeing some publications, first sketches. Johannes, a Polish astronomer, actually put it like a treatise or an atlas of observations of the moon. And then Boschevich, I guess, Roger, actually proved that it didn't even have an atmosphere. And then Franz Grususen, I practice these, but I'm actually came up with the concept and thought that craters were formed by meteor strikes. This was really neat. I've actually heard the term, but I didn't know what it was. But I've heard of the Great Hoax. But I guess there were, in 1835, there was these 6 articles written that were unfortunately falsely attributed to Sir Herschel, who was a big-time astronomer back in the day, that they were stating there were creatures on the moon that had wings like bats, and there were unicorns and all sorts of these crazy fairy tales, and it spread like wildfire from the Sun newspaper, and people believed in it, and it was just this huge hoax that that just was just a kind of a crazy story back in the day. And then, as we're kind of moving towards modern times a little bit, in 1920, Robert Goddard actually suggested, why are we not sending a rocket to the moon? So, to the moon. So, John F. Kennedy, 40-some years later, technology's there, rockets are there. Well, why aren't we sending people to the moon? So, we did. And just kind of a brief exploration, to actually the foundation of the science and information that goes into determining what the moon is made of. Not cheese. It takes exploration, and the rocketry and our science is what got us there. So so these are just kind of some of the highlights. I mean, the U.S. were the first attempt, 1958, lasted 73.6 seconds before it exploded, but at least we made that attempt. So that was kind of like that first push of sending something actually designated to the moon. And then a year later, the USSR had several missions that actually were the first successful. A flyby, they actually impacted something into the surface, and then also photographs. And the bottom left one, by the way, is the Pioneer with the first attempt. So the first successful U.S. was Ranger 7, ended up sending back 4,300 images. And the one on the right is one of those first up close images from a U.S. satellite. And as we keep moving into 66, Luna 9, which is another USSR probe, actually landed a soft landing on the moon and took pictures from the surface of the moon. And then 5 months later, Surveyor 1, which is in the bottom left of the screen, was the first U.S. to do the same thing. So this was kind of a neat one. The circumlunar mission, the first one to actually go to the moon, around the moon, and actually land back on Earth was called Zond 5, and it was another USSR. And they actually loaded it full, all sorts of, they call it biometrics, but essentially everything from algae, you name it. But there were actually 2 tortoises on board, and they survived. So in theory, they were the first ones to go up in space and come back and survive, which I did not know, which was kind of interesting. And then, of course, the same year, we actually had Apollo 8. So we had did the same thing with humans. And the bottom right picture is, if anybody that just, one of the most iconic images ever is called Earthrise, taken to actually see and have that perspective of how small the Earth it really is, from the perspective from coming around the side of the moon, is just spectacular. And then, of course, Apollo 11, the next year, don't really need to get into the Ingle has landed. We put a human put it on the moon. And then a year later, we had the first robot. So, Amy and I gave a talk not too long ago about Mars, and we're there, the rovers there are little robot geologists who we love. But actually, the first one was a robotic explorer from the USSR that traveled over 6 miles in almost a year, performing all sorts of different soil analysis and so forth down in the bottom middle. And then Deere and us, I guess, just because we're both geologists, in 72, which was the last mission and for humans on Mars, we sent a geologist. But duh, that's what you should do when you're trying to discover what the geology of our moon is. So, and more on that later. In the 80s, it was boring. It was quiet. There were no missions, nothing at all. And then once we got into the 90s, only 3 of them. Japan finally put the first one up. It had been the U.S. and the USSR up until that point. Into the 2000s, though, it started picking up again, where we have the U.S., Europe, Japan, India, and China. India and China actually put up their very first ones. And the Chandra, which if you look down below, really focused on ice and water. Huge array of all sorts of instruments that from scientific exploration on that. And then we'll kind of show this a little bit later, but there's a couple other satellites U.S. for the LRO and the L-Cross as well. And then moving into the last decade was mainly Chinese and U.S. missions again. It should work. There we go. But Israel actually sent their first one, and it was also the very first private company to send something that wasn't a federal or government sponsored program. Unfortunately, it was unsuccessful, but it was that first attempt by a private company. And then the Grail mission, as you can see on the bottom, where we actually did microgravity or did gravity to measure the density of the moon itself, to really help us identify how thick the crust is, and the variations of materials across the moon, which is pretty cool. And
okay,
off to Amy.
So why in the world would we want to understand anything about the moon? I think this quote sums it up pretty nicely by Heisinger and Jaumann. The moon is the Rosetta Stone for understanding the fundamental processes that drive planetary formation and evolution. And you think, well, why is that? Why the moon? Well, when you think about humans, as we know right now, we are the only living organisms, as far as we've explored, that we have detected. And the moon is right there for us. And we have the technology to go up and touch it, and to fly around it, and to monitor it. The beauty of the moon, and especially in our understanding of the solar system, is that the moon remains essentially a piece of untouched beginnings. So, for example, we have the Earth. The Earth is dynamic. The Earth is ever changing. And it started off in the same, well, we'll talk about how the moon started out, but there's key differences between the Earth and the moon beyond just its size and its relationship in space. But the moon has no plate tectonics. So where Earth is made up of a number of plates that move about and collide and crash into each other, and where new plates are getting formed in some areas and some plates are getting destroyed and recycled into the mantle. So there's an ever-changing dynamic surface. The moon doesn't have that. It's the same surface, mostly, that it's had since the beginning, since its formation. So it hasn't changed. It's still this piece of original material from when the solar system formed. There's no atmosphere, there's no hydrosphere, and there's no biosphere. All of these things, water, air, and organisms, they alter materials over time. So if there's none of those things that weather and alter and change materials, then we have the moon that, again, holds the original materials from its initial formation. And so that preservation is there. It's right up there. We can see it. It's preserving materials that have sat there essentially untouched for 4.5 billion years. So that's pretty cool. So what the Apollo program did for us is allowed us to touch the moon. So not just us going up and touching it, but bringing back materials for humanity to interact with and to measure and to detect the geochemical signature of. And so the Apollo 17 mission actually had a trained professional geologist on it who trained other geologists to be geologists. What the Apollo program did is it brought back a whopping 842 pounds of rock from the moon, right? And not just rocks, but core samples. So they dug 3 meters deep in one location to look at what's called the regolith, the surface mantle. I don't want to use mantle. The surface material of the crust. They brought back small pebbles in the sand that told us that the surface in some areas is this kind of glassy material that has kind of fused together from impact ejecta. So people did that. People went to the moon and brought back this information that scientists all over the world are piecing out and doing measurements on today. Also, we've sent the orbiters that have sensors that look at the mineral compositions and look for ice and for water on the moon. And they can map out an area in which the Apollo mission has sampled. And now other places that were remotely sensed with the same signature, we can tie or essentially, map out the processes as a whole for the moon. So for geologists, it's critical ground truthing, right? We can fly satellites and do remote sensing all we want, but when we have an actual piece of data that we can measure at a point, then we can actually construct much better maps and much better understanding of what's happening. And they set out sensors and detectors, some of them actually being seismic equipment. I read where there were seismometers deployed on multiple Apollo missions, and they detected moonquakes, which I'll talk a little bit about here in a minute. And so again, I think what's really important about the Apollo mission is that they understood the importance of having a trained geologist. And that was Harrison Schmitt with Apollo 17. And he was responsible for conducting the sampling and the geoscience aspect of those missions, and contributed to bringing back all that awesome stuff from the moon. So let's talk about the things brought back from the moon. So I've kind of broken down the rocks that have come back to Earth from the moon into kind of three types. One is a rock called, and each of these tell a story. So rocks aren't just rocks, they're actually pieces of the history of the place. So for example, the rock anorthosite, you're gonna see the word plagioclase feldspars thrown around in some pictures. And what this is a set of minerals that range in composition between being sodium rich and calcium rich. And so they're relatively light, mass speaking, right? Because these are lightweight atoms that build the structures. Also, the thing with this rock anorthosite is that it has big crystals. And when we, as geologists, see rocks with big crystals, it tells us something about how it cooled. So it came from magma, so it came from liquid rock. And because it has bigger crystals, it means it cooled slowly, which means that it cooled relatively not right at the surface of the Earth, but at some depth. So this rock anorthosite tells us the story about where it cooled. And so when we see the maps that have regions that are anorthosite, what that tells us about the moon is it's the older, more original material from when it originally cooled. Then there are rocks that are basalts, and these are rocks that are volcanic, and they tend to be more iron rich, and they contain minerals such as pyroxene that are more iron rich. They come to the surface as molten rock and they cool. So I almost said Mars, on the moon, they are in areas where liquid rock has come to the surface like at impact craters. So when an impact hits and it melts the crust, that liquid comes to the surface and it can cool as basalt. And then there's some other processes at work where basalt can come out to the surface. And the basalt on the moon is interpreted to have formed after that big initial cooling event from its early cooling off from a molten state. The third big rock type that I want to talk about is the breccia. And breccia is a rock that is made up of angular pieces of other rocks. So if you look closely at these two breccias, I like this one on the right, you can see chunks of material in it. So it's got different colored materials that are all chunked up. These form from processes like impacts. So where there's crustal material on the moon, it's hit by a meteor, and that broken ejecta fuses together from different parts of material that were involved into a new rock that's basically, chunks of the other rocks. So when we find the breccias, we think about the impact, the multiple impacts that have occurred to alter the surface of the moon. So before I get too much more into some really cool geologic features and what they tell us about what's happening on the moon, I want to talk about the hypotheses that are proposed for its formation. So there's 4 key hypotheses. There's what's called gravitational capture, fission, condensation, which is basically the accretion hypothesis, and then the giant impact model. So the gravitational capture hypothesis is the idea that the moon came from somewhere else, all right? And so maybe it was a larger asteroid or protoplanet that came near the Earth and got captured into Earth's orbit. And this would be similar to how other moon planet systems in our solar system occur, and how those moons were captured as to be part of the orbit of planets. This doesn't quite work for our moon, though, because the moon has different layers of composition that make up the moon itself, which indicates that early on in the moon's history, it was mostly molten, and that as it cooled off, it differentiated. And I'll talk about that in a later slide. And so if it's a captured body of an asteroid or a protoplanet, this isn't expected to be what we would see in the moon. There is some similarity to the composition of the Earth, but more importantly, the moon and the Earth are very similar in their age, which indicates there's something there tied together with their formation. Also, the moon is much larger than other planet to moon relationships. So it's a much larger proportion of Earth than others. And just the sheer size of the moon would make it very difficult to capture into Earth's orbit, of course, without colliding with it. The fission hypothesis is interesting and was proposed by Charles Darwin's son, George Darwin, who proposed that early in Earth's history, it was spinning so fast that it basically looped out a piece of itself. That's the best way I can put it, is that it spun, and from the equatorial region of the Earth, a piece of Earth kind of separated off and then remained in the orbit of the Earth. And George Darwin proposed that this region that it came from was the Pacific Ocean, right? And then, you look at the map, and the Pacific Ocean is this vast, wide, basalt-rich material on Earth. But this hypothesis just doesn't work. And it doesn't work, one, because the Pacific Ocean is, its maximum age is about 160 million years, because that crust gets recycled over time. So it's a relatively young feature on Earth that is constantly changing and is ever dynamic. And that there's no evidence in Earth's history of having such a spin that is required for that bloop to take place. You like that technical term? Yeah. Okay, and then third hypothesis, condensation, which is like the accretion hypothesis, which is the hypothesis essentially of how Earth also formed. So early on in the rotating disk of our nebula that eventually formed our solar system, you have gas and dust and particles that are colliding and coalescing and forming larger and larger bodies that as they grow larger, they have more gravity, so they're pulling in more material, so they grow in size. Well, this idea is that that was happening to Earth, and right next to it, it was also happening to the moon. Okay, so that these both formed from accretion at the same time. This doesn't quite work because even though they do have similar compositions, they would have nearly identical compositions. And we know that the Earth and Moon don't have those similarities. And also we'll find out here in a little bit that the Moon actually has a very small iron core. And if it were to have formed similarly to the Earth, it would be expected to have a much larger iron core. So out of the four proposed, the fourth hypothesis that seems to work with the data coming in is the giant impact model. This is a sexy model, right? You've got this planet coming in about the size of Mars. And this happens, and this is key. The timing of when this happens is key because it's very early on in Earth's formation. So when Earth is still hot from the bombardments and the building of the planet, it's still hot. It's still relatively mostly molten early on. And then you have this Mars-sized like protoplanet that comes in and just slams into Earth. And there's a critical piece to this in how this protoplanet hits, and that is it hits obliquely. It hits Earth obliquely. So it doesn't slam right into it head on. It actually hits it and scrapes off pieces of Earth. And this is critical in what we call the geochemical story, because Earth, the Moon doesn't have a big core because it didn't have enough iron early on. And the reason this model explains that, in that where the bulk of Earth's iron is in the core, right? So the core of Earth is both molten and solid iron and nickel. So early on, those materials sank to the center to form the core. When that Mars-like sized planet obliquely hit, it didn't really take much of the iron-rich core. So all the iron that the Moon got was just from the mantle and whatever was in the original body that did the impacting. So this model helps to explain the chemistry of the Moon. Okay, and it also explains the high angular momentum of the Earth-Moon system. It has a much higher angular momentum than any other moon-planet system in the solar system. So this is a really great short video that walks through and visualizes this impact hypothesis. So there's the molten early Earth. Hot. There's the object that has been named Theia, I believe is how you pronounce it. There is the impact. And then basically it's the accretionary processes take over now and particles begin to combine. I find the next statement pretty interesting, and I haven't read anywhere else about the timing of these events, but this video from the American Museum of Natural History seems to say this process happened in about a month. So again, I haven't read much on the actual timing of this, but that's pretty interesting. Okay. So what this impact model hypothesis does is it explains that high momentum, it explains the minimum iron core and the size of the moon relative to Earth. Initially, when the model was proposed, there was a lot of trouble in modeling this. So you're talking about modeling an Earth-Moon system, which has its challenges, right? To scale up a model to that size. But with technology, with computing power, and also with just the data we're receiving from the moon, the geochemistry, that can be modeled to produce a more quantitative understanding of what happened rather than a general, it hit, it spiraled, it formed, qualitative understanding. And so the more data we collect from the surface, the more goes into the model to fully understand and support or not the impact hypothesis. So here's a screenshot from a paper where there was a mathematical model done. There's the obliquely hitting Mars-sized planet hitting Earth, and then the eventual formation of that cute little moon right there. Okay, so this is about a 5-minute long video that is worth the watch, and it kind of introduces us to surface features on the moon, and I'm going to talk just about a few of them. But really what I think it does is it shows us how outstanding the data from the Lunar Reconnaissance Orbiter, the LRO, has been in our understanding of the moon. And there's some really great imagery that we can't miss. So we'll watch this.
Question.
Yeah.
What happened to the impacting body?
It melted essentially and became part of the material that then was broken up and coalesced. So I think that what that does is it helps to explain some of the differences in geochemistry as well.
But it's described as a Mars-sized body.
Yeah.
It's much bigger than the moon.
It is. I would expect that maybe, that's a good question.
Well, I would think some of that would have come in and incorporated itself into the final product of Earth, and some of it got blown outside the orbit.
True.
Yep.
Yeah, absolutely. It's a really cool hypothesis to think about and to see the models of.
And that explains how I got here. No, that was my ship. No.
Amy, is there narration on this? Because I'm not hearing it.
There is. Can you hear it?
Amy, is there narration on this? Because I'm not hearing it.
There is.
No.
Okay.
Well, maybe
Can
you'll
you
have
hear
to narrate
it?
yourself.
Oh, I'll try to relate. So they just showed the Oriental Basin and the gravity measurements that were overlaid on top of the Lunar Reconnaissance Orbiter mission. And then, oops, I'm hitting buttons, it's not working. And now we're zooming into a crater that they were able to detect the actual size of it through the instruments on LRO in an area where they've detected ice. And then they're moving to the South Pole Aitken Basin, which is a very large impact region. And this is revealed through the topography that the LRO has shown us. And with the LRO, we're also able to see in detail the far side of the moon, which is pretty cool. And so this to me is the most interesting part they're going to zoom into this impact crater. And in the center peak, they're going to zoom into a boulder that's sitting on top of this peak that's about 100 meters in size. But this is there's the boulder sitting right in the center of that peak. So you can see the detail of the orbiter imagery that then they combine with other remotely sensed data. And so basalt basins that have mineralogy revealed to us. So there's different types of rocks and different types of minerals that are highlighted in different colors. So we actually see the mineralogy of the surface of the earth. Oh, the moon.
That's what I'm here for.
And then they go into one of the Apollo landing sites and are able to actually see the tracks of the vehicles. And this is the Apollo 17 site where where the geologist was. That's what's important. And you can actually see the bottom part of the craft that remained. That's the lander.
Wow.
And the rover vehicle is still there and it's imaged. So it's really pretty interesting, the technologies we have to remotely sense the data. So they end the video with showing, kind of thinking about the future and where, in planning on bringing humans to the moon. And so in this area, they've analyzed where sunlight basically hits versus shadow, where solar panels may be placed to provide energy for humans as they occupy the moon. So it is pretty cool, and I'm sorry we didn't have the volume for that. But okay, I'm going to try to move on here. So just some LRO imagery, the topography, again revealing the terrains and the large impact craters on the moon. The USGS recently, just a few years ago, published their geologic map of the moon, put together from the LRO and the geochemistry data, the samples collected by the astronauts. And so we now have a geologic map of the moon. Different terrains are represented by the different rock types that are present. And so, for example, there's really two big terrains that occupy the surface of the moon. And they are the creep terrain, which is also called the PKT. And interestingly, this really is about the chemistry. So that stands, the K is for potassium, the REE is for rare earth elements, and the P is for phosphorus. So that creep terrain is saying something about the chemistry of the rocks. So there's the creep terrain, and then there's the feldspathic highlands. And these are some of the oldest areas on the moon that were remnant from when the moon cooled from its original molten state. So speaking of that, we get into this idea that early in the moon's history, it was mostly molten and what they refer to as the magma ocean. And this image over there is showing how it chemically differentiated as it cooled. And I've got to back up and go back into it to see it. But early on, as the liquid magma cooled, crystals settled out, and the heavier crystals were more iron-rich and physically heavier, so they dropped down to the center, and the lighter materials ended up floating and becoming the thick crust of the moon. Interestingly about the moon's crust and how it differs from the Earth is that it doesn't have plates. It's just all one crust. So you don't have these broken plates like Earth does that move about with each other. There is a crust, there is a mantle to the moon, and there is a very small core that is iron rich. But again, there's no plate tectonics, and I read somewhere where they referred to it as a one plate planet. So those seismometers over the years have picked up a number of moonquakes. And these are not necessarily plate tectonic related, but they can be separated into 3 different types: deep moonquakes, shallow moonquakes that have to do with some surface contraction and extension, and then the quakes that are caused by impacts. And so these seismometers that have set up on the moon have detected over 13,000 of these types of events. And with that, it also helps us to understand the deeper makeup of the moon. And if we can get them spread out more, like if we got some seismometers on the backside, we would have a much better understanding of the actual interior layers of the moon. So some of the moon's known for its craters. And I found this interesting, kind of the classification of craters on the moon and the characteristics that they tend to have. So there's 3 kind of general groupings of craters depending on their size and what features they hold. You can have anything from microcraters, and then up to about 18 kilometers diameter, they have just a classic bowl-shaped topography and with just very simple featured craters. When you get up to 18 kilometers to about 100 kilometers in diameter, the features change to have a steeper rims, and they have terraced rims, which are these big faults that form during the impact and then later settling of the crater. And they have a centralized peak, like the Tycho crater with the boulder on the top. In fact, that's Tycho. That's what the video showed with the boulder. So they've got central peaks, and then they've also got these plains of basalt. So this is where the impact was so great that it melted the crust. It became molten and flowed out, and basically there was a lava flow that cooled. And so out around these peaks are flatter parts of the inner basin. And then when you get into the greater than 100 kilometers sized impacts, you're getting these massive features that are pretty broad and flat, but the rocks and crustal materials are inclined from the impact, so we can see the progression of the layers as we move out from the center. And so here's an example of the Oriental Basin, which was the first big basin shown on that video where they overprinted the gravity, the colors. And you can see where there's the basalts that flow into it from the impact, the melting. Here's the rim and these types of faults that cause these different layers around the edges of the rim. But you can see that they can be pretty complex in their features. But they also, what's great about impacts is they also reveal to us what's underneath, right? They excavate so that we can see what's going on deeper into the crust of the moon. So there's volcanism, and interestingly, it's a little asymmetrical in terms of where we find the volcanic processes occurring. The near side has far more volcanic rocks than on the far side of the moon, and that's shown in this image here. There's a bunch of volcanic features like lava flows, cones, and what we call pyroclastic material, so material that's been blown out in a molten state onto the surface of the moon. Interestingly, there are also lava tube collapses. And this is one of those where there's a lava tube in the subsurface. And so lava tubes are hollow and the surface has collapsed down into it. And this imagery is revealing the pit floor of the lava tube. And with the technology, they could actually even see its depth. And so this is like, these are all, this tallied up is how many meters is represented here. And I did the count and I can't remember what this sums up to be, 30 something, I think. Meters deep is what's shown, at least in this image. These become pretty important when you're talking about humans occupying bodies outside of Earth, because these are places of protection from solar radiation. And so I know that they're actively looking for these on Mars, right, for humans to go to as a safe haven to be protected from that harsh environment. So there are I'm going to conclude my part with just a couple more features that say something about the activity on the surface of the moon, and kind of like tectonics, but not really. And these are basins that we call grabens, and that's the same term that we use here on Earth. But a graben is a feature. It's like a depression, a linear depression, where this side here with my arrow, if you can see it, is higher, and this side is lower, and then this side is higher here. It's like a drop-down basin that occurs when the surface is pulled apart. So when there's extension. So we know that in areas that we find these grabens, that the crust is being pulled apart in these areas. So what exactly is causing that? I'm not sure. There's this known set of processes that are doing that. But I know there's ideas that many of these are found around impact craters. So there can be some extensional stress around impacts and to cause these grabens. I think the more interesting feature, and here they are again. So this is one of those, what they call a rill here, but it's a graben feature where it's down dropped from the pulling apart. These are super cool to me, and they are similar to features we see on Earth where there's compressional forces. So where things are getting pushed together, compressed, and in order to accommodate that, you have to put material on top of other material. You have to pile things on top of each other. And one way that this happens in brittle materials is through faulting. So developing a fracture, and then the material moves up and on top of the other material. There are these types of scarps that show thrust faults on the moon, and they're considered some of the younger features on the moon. And one idea is that they are there because of the shrinking diameter of the moon as it cools and shrinks. That as it cools and shrinks, all the material that exists has to go somewhere. So these thrust faults form that push material on top of other material to accommodate essentially the squishing. Now, interestingly, extensional features like grabens don't support a shrinking moon, right? Because that's telling us about extension. So I think there's still a lot to be worked out here. This is what these look like. So on Earth, we see these a lot in areas that are active with faulting. In the subsurface, you've got this material here moving up on top of this material to accommodate that compression. This is what that looks like on the moon. So this area here is lower in elevation and this area is higher. So this material has actually been pushed up on top of this material. And if you zoom into the image right in this box, our cat wants to listen about the moon. So you can see where there are craters that have been covered by this material. So again, these are pretty relatively recent features on the moon. I think within the past billion years is what the word on the street is. But this is where I end my discussion of, features on the moon and geology of the moon. And I'll leave us with this about a minute long. It has no sound to it. A view of one of these scarps. And so on the left here, this is the Lee Lincoln scarp. On the left here, this is material that's been pushed up and on top of this material on the right. So things are getting pushed together and piled up. And that's really cool. So a nice little flyby there. Okay, and so that's where there's a lot of more stuff to talk about the moon, but we're out of time. So I'm gonna let Kevin close it off here.
Go on and on about geology. So just two last slides, just to kind of wrap things up. Just because we've, where we're at now, night and day, obviously, from where, as science and how it's evolved, but there's so much still to learn. That's why these are all called hypotheses. So we're still learning and trying to test them and find out more information. And just kind of one of the big ones that's coming, is the Artemis program or the Artemis missions, where we're planning on bringing humans finally back to the moon. So the goal is 2024. And it's just some of the basic science goals, of course, understanding just in general planetary processes, their volatile cycles that are involved. Of course, the impact history of that whole Earth-Moon system itself. I'm not quite sure about this one, but revealing the record of the ancient sun.
Yeah, so there's a lot of complex stuff going on with the weathering of the surface of the moon and how solar radiation has impacted it over time. So I suspect maybe they're going to be doing that, and also setting sensors out because there's no atmosphere to, prohibit, that direct connection to the sun. So.
Yeah, I mean, observing the universe from a unique, imagine putting a telescope on top of the moon.
That's a sure way to get rain on the moon.
Yeah.
You can buy all the telescopes you want. You don't have to worry about clouds. But just think about, there's so many unique opportunities there about conducting different experimental sciences. We've got the International Space Station that we're doing all these things on, and imagine being able to take that into a more permanent locale as far as being on the moon. And of course, seeing, how much that affects humans themselves, like the International Space Station, just as far as, the other thing is, it's field geology. We're hopefully going to send more nerdy geologists up to the moon and to be able to see more than just a few.
I would love to be that person right there.
But more data is always better, and so we're just picking right now. We've just got a few trips that have brought back just a handful of rocks. Just imagine being able to go around the entire moon and just sample, and pick and choose based on those geology maps that are currently made, and fine tuning those and really learning more. And of course, adding more instrumentation and so forth. And then access to the far side as well. And it's not in here, but, and lastly, this is a stepping stone too for exploration for the rest of the solar system. So if we can get things to the moon and launch from there, it's a whole different ballgame when your gravity is 0.16, on the moon compared to here. Just all sorts of stuff. But of course, geologists have a really big key role in all that. So,
so
and that's it.
That's what we put together. And I'm sorry, it feels like it was a little long, but I learned a lot, and I hope others did as well. So, I think.
This is George Bill. I have a question.
Yeah.
When I was working, I'm retired now, but one of our retired NASA engineers from the Apollo missions told us that the real problem with going back to the moon is not getting there, not landing, and anything like that, but it is the dust that is there that gets into everything.
Oh yeah.
It said that they have really not solved that problem yet. He said when they brought back the samples, all the samples were supposed to be in airtight containers, and the dust destroyed them. So I was wondering if you heard anything about that.
No, I didn't read anything about that, but it makes a lot of sense. If you look at Mars and the initial idea with the rovers, and they thought, for example, Spirit and Opportunity would only rove for 3 months, right? And they ended up lasting for over a decade because they had winds that would clean off the solar panels to allow for the sunlight to come in. The moon doesn't have an atmosphere to cause winds. So that I could see where that would be a major problem. And that fine glassy dust that makes up the surface could be a real issue.
You look at the photos that we showed earlier with Schmidt on there. He is filthy.
As a good geologist should be.
Well, of course.
Yeah.
Yeah.
The problem is it actually destroys all the seals. And they have a lot of problems. It's a very abrasive dust. They're really still, I guess they're still working on it. I haven't heard if they solved that.
I'm sorry. I didn't come across anything like that.
So I'm going to kill the live feed. Thank you, everybody, for joining us. Members, you can stay in the feed and talk. Thanks, everybody, for joining us. If you have any questions, feel free to type it into the chat or on the video that we posted there, and we'll see you next month. Members, stick around.
See you next month.